In this video, I want to talk about how we can calculate the frequency response of differential equations. We already looked at how differential equations are related to the Z transform. But what if I want to find out what is the frequency characteristics and what is it doing in the frequency domain in terms of the frequency variables, either omega or f? How do I know whether a particular transformation is behaving like a low pass filter or a high pass filter? So what transformation is happening? So we've already seen that if we have a difference equation yn equal to m, let's say m equal to minus infinity to infinity x n minus m, and let's say you also are multiplying some, you're also putting some weights when you're doing this transformation. So these are given by a. Now if you convert this into the z domain, what we get is yz equal to summation m equal to minus infinity to infinity, and you can say x z z to the power minus m a m. Okay, so that would be your z transform of this signal, of this transformation. And therefore you can write the transformation that is happening, the transfer function of your system, as xz over yz. Because this xz does not depend on m, we can take it out of the summation, and therefore this becomes m equal to minus infinity to infinity am z to the power minus m. Now that reminds me that I think I've made a mistake here, and maybe you should be careful here as well. So this should not be minus infinity, right? I want this to be 0. Remember that? Why can't we have it as minus infinity? Why can't we have m as negative? Because then we are actually saying we want future signals to process and get the present output. And that is probably possible in some situations. For example, your entire input, let's say you're recording ECG signal and you have already recorded all the ECG and put it in memory. Then when you are trying to get the output at a particular instant, you have the future inputs because you have all the signals stored, and the previous inputs in the system. But in general, when you're making systems, you really can't have the future, for what the input is going to be in the future. Your output at the present time has to depend on the output at the present time, sorry, the input at the present time and the input in the past times. It cannot depend on the future inputs, right? So that's why m should be 0. Now, so this is kind of the Z domain representation of what your system is. So if you can evaluate this, you can get the Z domain representation. Now, how do you go from here to the frequency domain representation? So let's say this is called, let's say hz. Just the transfer function is called hz, and what I'm asking you is, how do we go to h, um, and I'm going to give you a clue here, e to the power j omega. Remember when we discussed this a few videos back, we said z, we substituted e to the power j omega, or z, instead of e to the power j omega. So if we do this substitution in this equation, what do we get? So we get h e to the power j omega equal to m equal to 0 to infinity am, and instead of z we say e to the power j omega to the power minus m, so I can write it as this. So for our particular system hz, we get our frequency domain representation like this, and this kind of gives you how the frequency domain of the system would look like. And if you are able to get the frequency domain representation, and if you can then, once you get that, if you can plot on the x-axis your omega, and on the y-axis you plot h e to the power j omega, and that will kind of give you what kind of transformation is happening, right? And in the next video we'll do that, and we'll check out what a few simple transformations do.